welcome to T Academy. In today's lecture, we'll learn how to apply Thevenin's theorem on a circuit with independent voltage sources. So Thevenin's theorem can be applied if we have a circuit A which is connected to another circuit B. More often than not, B is the load across which we are asked to find out the voltage, and the condition here is that circuit A has to be linear. Then we can replace circuit A with a Thevenin's equivalent so long as the current that flows from circuit A towards circuit B remains the same. And in order to replace this circuit A with a Thevenin's equivalent, we connect an open circuit voltage VOC in series with a Thevenin resistance, and this Thevenin's equivalent is then connected to circuit B, and since the current remains the same, the drop across the load B doesn't change. So this principle will apply to this circuit with independent voltage sources. I already made one lecture on Thevenin's theorem when it is applied to dependent voltage sources. So you can click the link in the description to see that lecture if you have missed it. So there we applied Thevenin's theorem to find out the gain of an amplifier circuit. So in this circuit, we are asked to find out the voltage across the 6 kilo ohm resistance. So this we identify as the load, and everything to the left of the load we can consider to be circuit A, and the load 6 kilo ohm as circuit B. So let's see how we can represent circuit A in terms of an open circuit voltage and a Thevenin's resistance. So first we start off by finding the open circuit voltage developed at the points where circuit A meets with circuit B. So we need to open the circuit at these two terminals. So let's redraw the circuit. We have our 1 kilo ohm resistance here, then the 2 kilo ohm resistance, a 2 milliamp current source, a 3 volt voltage source, and then we open the circuit at these two terminals. And now in order to find out the Thevenin's voltage or the open circuit voltage, we need to find out the voltage developed at these two terminals. Now since this 3 volt voltage source is not connected at this point, no current can flow through it. Thus all of the current pumped out by this 2 milliamp current source has to flow through the 2 kilo ohm resistor and the 1 kilo ohm resistor. Therefore, the drop across the 2 milliamp current source is simply 2 milliamps multiplied by the series combination of 2 kilo ohm and 1 kilo ohm resistor. So we can find out this voltage V1 as 3 kilo ohms multiplied by 2 milliamperes, and this comes out as 6 volt. And then the open circuit voltage at this point is simply the addition of the 3 volt voltage source and the 6 volts developed across the current source. And our open circuit voltage comes out as 9 volts. Next we proceed to find out the Thevenin's resistance looking back from the point where circuit A connects with circuit B. here as well we have to redraw the circuit by opening the terminals where circuit A connects with circuit B. So we need to find out the equivalent resistance looking back from this point into the network under the condition that all current sources are open circuited and all voltage sources are shorted. Therefore, we open this 2 milliamp current source and we short this 3 volt voltage source. So let's redraw the circuit. We have the 1 kilo ohm here, 2 kilo ohm resistance, and then this current source is open circuited and the voltage source is shorted, and we are interested in finding the equivalent resistance looking back into the network from this point. And this is simply the series combination of these two resistances, and this comes out as 3 kilo ohms. So now that we have found out the open circuit voltage as 9 volts and the Thevenin's equivalent resistance as 3 kilo ohms, we can replace circuit A with this Thevenin's equivalent and connect this equivalent circuit to the original load of 6 kilo ohm. So this point is connected to the load, and we were asked to find out the voltage across the 6 kilo ohm resistance, which simply from voltage division can be found out as 6 over 3 plus 6 into 9, and this comes out as 6. So I hope with today's lecture you understood how you can apply the Thevenin's theorem on circuits containing independent voltage sources. So just to recap, in order to apply the Thevenin's theorem, we need to have a linear circuit A which can be represented in terms of an open circuit voltage and a Thevenin's resistance, and then we can connect it to our circuit B, which in most cases is the load. In order to find out the open circuit voltage, we have to open the circuit at the terminals where it connects to the load, and then we have to find out the open circuit voltage developed at those points. For the Thevenin's resistance, we need to look back into the network from those open terminals and find out the equivalent resistance under the condition that all current sources are open and all voltage sources are shorted. And then we can replace the original network with this Thevenin's equivalent and then proceed to find out the voltage across the load. So that's it for today's lecture. I hope you found the content interesting. Feel free to visit my channel for other videos related to circuit theory, signals and systems, electrical machines, and many other courses that I have on my channel. And please like and subscribe to the channel if you like the content, and I'll see you in another video.